This week we're going to be talking about circuits. This is probably something that you've done before in maybe junior high or grade 5, I think. But we're going to look more at some of the calculations involved with these circuits. And these are very simple calculations. Now, the circuits are super important in kind of all the technology we use. Here you can see a picture of a circuit board with a chip. Fundamentally, circuits kind of work the same at the same level all the time. However, they just get more and more complex. But the foundational rules, the simple rules, are still used for a majority of the circuits that we use today. Now, there are three quantities that we need to be aware of. The first is voltage. Voltage is kind of a measure of potential energy. So voltage is the ability to do work. A common example that people kind of talk about is like a dam. So if we were to have a dam and all of this water kind of behind the dam, it's able to do work as we open the dam and let that water actually flow out. So voltage is the ability to do work. It is measured in volts. Current is the flow of electrons, or it's the flow of electricity. So if voltage is the dam or the potential energy, the current is what we get when we actually open the dam and allow that water to flow out. Current is measured in amps, so it's the amount of charge that we have flowing per second. And so voltage and current are very closely related. Voltage is the ability to do work, and then current is the amount of charge we get actually flowing through the wire. If we have a lot of current, that's a lot of charge. If we don't have very much current, that's not very much charge. Tasers have very high voltage, but very low amount of current. So it's the current that will kill you is kind of what the saying is. The voltage will not necessarily kill you. It's the current that grabs onto you and will actually cause harm. So it's the amount of charge. The last quantity that we need is resistance. Resistance depends on the materials. Sometimes we want resistors to help protect some of the stuff in a circuit. But resistance is how easily electrons can flow through that material. So is it something with a high resistance like wood, or is it something with a low resistance like copper, which would allow electrons to flow very easily? Resistance is measured in ohms. So that's measured in ohms. Current is measured in amps. And voltage is measured in volts. Now, all of these are linked together in the equation V equals IR. And this is an equation we're going to be using for making calculations this week. So we can find any of these quantities if we know the other two. So here we have two different types of circuits that you've probably learned about before. There are series circuits where electricity follows one path, and then there's parallel circuits which have more than one path. Now, in both of these types of circuits, we can still use this equation, V equals IR, but there is a difference between the circuits in how we calculate resistance. To find the total resistance for a series circuit, it is the resistance of the first thing that's exhibiting a load plus the resistance of the second thing. That's the total resistance. Whereas for parallel circuits, we have this inverse equation where 1 over the resistance total is equal to 1 over R1 plus 1 over R2. And there are differences between them. In a series circuit, you'll notice that as I increase the voltage, this LED comes on first before the one after it. So there are voltage drops as we go across these loads for a series circuit. The other thing with the series circuit, if I were to remove this one component, now the circuit doesn't work. The circuit is incomplete. So in order for a series circuit to work, it needs to be hooked up. Everything needs to be functioning. If I remove something, then the circuit will not be complete. For a parallel circuit, now I don't need as much voltage because there is not a voltage drop across the first one like in a series circuit. So for a parallel circuit, the other benefit of a parallel circuit is that if I were to remove one of these components, the circuit still works. So if I were to remove this component, that bulb stays lit. If I were to remove this component, the other bulb stays lit. So there are some advantages to parallel circuits. I learned this Christmas that my Christmas lights were in a series circuit, and it took a lot of time to try to find which bulb it was. Whereas our indoor Christmas lights were a parallel circuit, and we had some nice lights even though a couple were out. When we draw circuits, there are some diagrams that we are going to need to be familiar with. Now these are in your notes for this week. You can also come back to this point in the video if you want to look at it. But wires are drawn just with a straight line. When we look at joining wires, we draw connections with those dots. Switches, you see, can be open, and we draw them as open so we know that they're there. When we talk about a cell or a DC power supply, we draw it with a long line and a little line. The little line is the negative side. The large line is the positive side. That's how we draw a cell. A battery is a combination of cells. So if we have more than one cell, then we have a battery. In this battery, you see we have 1, 2, 3, 4 cells. If each cell is 1.5 volts, then this battery is 6 volts. A resistor is something that we'll be using in kind of the examples this week, but you'll see in a resistor as this jagged line, a zigzaggy line. A lamp looks kind of like a flame inside of a circle. These other ones, so a voltmeter, an ammeter, and an ohmmeter, are used to measure. So a voltmeter measures voltage, an ammeter measures electric current, and then an ohmmeter measures resistance, and you'll see them drawn that way with their quantities drawn inside of the circle. So these are going to be important for this week's assignment. And it helps us to just communicate, but you can go back to this reference in your notes this week. So here we have a question. We want to find the total current and the voltage drop across the 73 ohm resistor. So we have here a series circuit, and we can come at this a couple of different ways, but let's first calculate the amount of current that's flowing through this circuit. For a series circuit, the amount of current flowing through this circuit is the same at all points. So we have that current is the same at all these points, and then we can calculate the voltage drops by using our total voltage and our total resistance. So let's first calculate the current. So because this is a series circuit, my total resistance is the sum of resistance 1 plus resistance 2 plus resistance 3 plus resistance of the fourth resistor. So 65 plus 84 plus 73 plus 10 is my total resistance for this circuit. So I go 65 plus 84 plus 73 plus 10. The total resistance for this circuit is 232 ohms. Now, if I want to find the total current, well, I have V is equal to I times R. Current would be my voltage divided by my resistance. So my voltage is 25 volts divided by my resistance of 232 ohms. So I have 25 divided by that, and I get a current of 0.1 108 amps. So my current, my total current for this entire circuit is 0.108 amps, and that will be the same across all of these resistors. If I want to find my voltage drop across this resistor, well, then I have this equation. My voltage is equal to current times resistance. So my current, I know, is 0.108 amps, and the resistance across this one is 73 ohms. So my answer times 73 gives me a voltage of 7.87 volts. So I know across this resistor, the voltage is going to drop by 7.87 volts. And that's because these electrons are doing work. So as I go across here, I do 7.87 volts of work, and now that voltage is gone. So the voltage is going to drop across all of these resistors. If I were to measure the voltage from this point to that point across the first one, I would have more voltage than if I were to measure from this first point to across this third one. So the voltage is going to drop across each of these in a series circuit. Here now we have a parallel circuit. If I wanted to find the current across R1, R2, and R3, we can treat them like they're series circuits. So let's do that. So if I want to look just for R1, I got V is equal to IR across this first circuit here. My voltage is going to get 12 volts. It's going to be the same voltage across all of these resistors. Divided by my 1 ohm gives me a current of 12 amps. If I want to look across R2, again, V equals IR. If I want to find current across there, so now I'm going to have that 12 volts across that 2 ohms. So my 12 volts divided by 2 ohms, and I get 6 amps. And then finally for the third resistor, take my voltage of 12 volts, I divide by 3 ohms, and I get 4 amps. So if I wanted to find the total current, what I can do is I can add up the current across each of those resistors, and I would get 12 amps plus 6 amps plus 4 amps would give me 22 amps. Now there's another way to do it, and that's to look at this total circuit. Let's do it that way. So let's first find the total resistance, where 1 over the total resistance for a parallel circuit is equal to 1 over R1, so that's 1 ohm, plus 1 over R2, so 2 ohms, plus 1 over R3, so that's 3 ohms. So I do this in my calculator. I get 1 divided by 1 plus 1 divided by 2 plus 1 divided by 3. And I get 1.83. Now that is 1 over RT. So I need to hit the x minus 1 button, or take the reciprocal of it. So if I go x minus 1, I take the reciprocal of it, and I get a total resistance of 0.55 ohms. There's my total resistance. If I wanted to now find the total current, I can use V equals IR. So I take my voltage, my 12 volts, divide by my total resistance, 0.55 ohms. So I get 12 divided by my answer, and I get 22 amps. So I can also find the total current by finding the total resistance. Now for a parallel circuit, our equation is different. But then I can use V equals IR to find my total current, which is the same as if I were to treat each of these circuits as their own individual series circuits and then total those currents together.